So we are starting out the class on Chapter 11. Chapter 11 is fluids, and we will discuss the ideas of pressure and buoyancy. Those are the two main topics we'll talk about in Chapter 11. We won't go through everything in this chapter, but I'm hitting the essential parts that I think are of the most interest of the people that are taking this class. So that said, I'll go ahead and get rolling on this. Before we talk about pressure, we actually need to remind you of the concept of density. So this specifically says mass density, but normally we just think of this as density. The reason we put mass in front of it is because we could talk about different kinds of density. We could talk about charge density or number density. At any rate, there's a couple different densities that show up in physics, and we put the word mass in front of it just to make sure that we know which density we're talking about. But this is the regular density that you're familiar with from chemistry class or prior schooling. So the density of an object is represented with this curvy P there. It's actually not a P, it's the Greek letter rho. And density is mass divided by volume. Now, the SI units of density are it's kilograms per meter cubed. This is a little bit different than chemistry class. Chemistry operates in grams and centimeters. So the SI unit for density the unit for density in chemistry is grams per centimeter cubed, but we don't use that in physics. We use kilograms per meter cubed. So density is mass over volume. Okay. So here's a table of densities. I don't want you to remember all these or anything like that, but I do want to highlight one specifically, and that's what is it? Water right there. So water is 1,000 kilograms per meter cubed. That's its density, and you might right away notice something a little different there because you might have had to deal with the density of water in chemistry class, and you might remember that the density of water is 1. Well, it's 1 if we're operating in grams per centimeter cubed, but again, we don't do that in physics. It's kilograms per meter cubed, and as a result, all of those densities that we might have come in contact with in chemistry are off by a factor of 1,000 when we talk about them in physics. So water's 1,000 kilograms per meter cubed. You don't necessarily need to memorize that, but it is kind of a handy reference point to have. All right. So moving on from there, if I can, there we go. Let's try and use this idea of density to answer a question. It says here we've got a man whose weight is 690 newtons. And this man has 5.2 times 10 to the negative 3 cubic meters worth of blood inside of his body. What we want to do here is we want to find the blood's weight, and we also want to express it as a percentage of the body weight. Okay. So let's see. In order to find the blood's weight, let's first off remind ourselves of what weight is. Weight is mass times gravity. That's if we could remember that from our last physics class, weight's mass times gravity. So if we want to know the blood's weight, we need to know its mass. And we don't have its mass. So what we have here is we have its volume. So we have its volume. But we know that density is mass divided by volume. So we can rearrange this equation. And if we rearrange this equation, we will get mass is equal to density. I don't know why that does that. Makes those funny streaky lines, but it's got something to do with my computer. So I apologize for that. But mass is density times volume then if we rearrange that equation. And on the previous slide, we had that table of values. One of them actually was the density of blood. So if we pop that in, the density of blood is 1,060 kilograms per meter cubed. And then we're multiplying that by the volume of blood, which is 5.2 times 10 to the negative 3 cubic meters. Okay. ran out of space there. But when we do the math, we end up getting that the mass of blood inside of this man is 5.5 kilograms. So 5.5 kilograms, that's roughly, what is that? Somewhere a little larger than 11 pounds worth of blood that we actually have inside of our bodies. And that's a legit number. That's so if you didn't know, that's how much blood you have inside your body, approximately. All right, so that's the mass of the blood. But what do I want? I actually want the blood's weight. So that's our goal. We want to figure out what the blood's weight is. Well, weight, again, is just mass times gravity. So if I plug those numbers in, the mass of the blood is 5.5 kilograms. G is 9.8. And if I multiply those together, I get out that the weight of the blood is 54 newtons. Okay, so we've got 54 newtons worth of blood inside of our body. All right, that's the answer to part A. Let's see, in part B, we're asked to figure out what this is as a percentage of the person's total body weight. So hold on to that number, that 54 newtons, and we'll figure out part B here. So in order to do this, we just need the weight of the blood divided by the weight of the man. Well, now I'm having all kinds of issues. Okay. Divided by the weight of the man. Okay. So we've got 54 newtons is the weight of the blood. 690 newtons is the weight of the man. And let's see, this gives us 0.078. And of course, if I want that as a percentage, then I need to multiply that by 100. And that gives me 7.8%. So there we go. It turns out that 7.8%, almost 8% of our body weight comes from blood. So that's something. If you didn't know that already, that's, you know, not only have you learned maybe a little bit of physics, but you've learned some biology too. So that's kind of cool. All right. Let's make sure that I'm right here. Yeah, okay. 5.5 kilograms worth of blood. That blood then has a weight of 54 newtons if we're here on Earth, where the gravitational acceleration is 9.8 meters per second squared. And then, yes, that's 7.8% of the person's total body mass. All right. So that was an exercise in density. We're going to move on now to pressure. The pressure that a force exerts is equal to the force divided by the area that it acts over. Well, that's great, but what does that mean exactly? So I've got a book in my hand here, and I can press my hand against the book and exert some force on the book with my hand. Well, now if I knew the area of my hand and I knew the size of the force that I was exerting, then I could figure out the pressure on the book just by dividing the force that my hand's exerting by the area of my hand, and that would give me the pressure that I'm placing on the book. So pressure is force over area. Okay, so some object is exerting a force on some other object, and if we divide that force by the area of contact, then we'll have the pressure on that surface. Okay. The SI unit of pressure it's a special unit. It's called the Pascal. It's a Newton per meter squared. That's force divided by area. Newtons divided by meter squared gives us pascals. Normally, when I bring up the word pressure, the unit that comes to mind is PSI, pounds per square inch, and we think about tire pressure. And that's certainly a legitimate unit for pressure. It's just it happens to be the I don't know, our unit here in the US, but SI unit, the metric unit is the Pascal. There's other units we might run across too. I use torr a lot in my research in vacuum science for historical reasons. We also know about pressure in terms of millimeter of worth of mercury, which we might use in the medical field, or maybe when we're dealing with weather. Yeah, in those units again are fine. And if we need to convert, we can convert. We can look that up, enter it into a calculator, whatever. But the SI unit of pressure is the Pascal. All right. So let's take and apply this a little bit. So I want you guys to picture me balancing on 1 foot. So I'm about 70 kilograms, and I balance on 1 foot. I want to know the pressure that my shoe exerts on the floor if all the weight of my body is balanced on that 1 foot. All right. So in order to do this, let's see, we can just pull out our equation. Pressure is equal to force divided by area. Okay. Well, what force is it exactly that's acting? What's the size of the force that's pressing down on the floor? Well, the size of that force is equivalent to my weight. And we remember that weight is equal to mass times gravity. So that was from the blood problem, but we also remember that from physics 1. So weight is mass times gravity, and then we're dividing by the area of bottom of shoe. Well, that's great. I've got the mass. It's 70 kilograms. I know G is 9.8 meters per second squared. That's my gravitational constant for gravity on the surface of the Earth. But I don't have any kind of measurements for the area of my shoe, so I need to come up with something here. But it does say estimate, and let's see. A person's foot, is approximately a foot long. That's about how long my shoe is. It's about a foot long. Yeah, I don't know. It's roughly, I don't know, about 3.5 inches wide or so. So what we can do is we can say that, we can approximate the bottom of my shoe is a rectangle that's got a length of 25 centimeters and a width of 8 centimeters. So if that's the case, then the area of a rectangle is length times width. And this will be, now I can't operate in centimeters. I have to operate in meters because that's the SI unit for length. And so I want my area in meters squared, not in centimeters squared. Okay. So always have to convert to SI units. So that's the area of the bottom of, that's an approximation of the area of the bottom of my shoe. It's 0.02 square meters. Okay. All right. So now that we've got that value, let's go back to here, and we can plug in my body mass and G and the area that we just figured out. And when we do all that, we get out a pressure value that is 34,000. Oops. It figures. Yeah, if I could back up now, I would love to, but I stuck myself. But the pressure is 34,300 pascals. So I guess if you have to rewind the video a little bit, you have to rewind the video a little bit. Sorry about that. So 34,300 pascals is the pressure that my foot is exerting on the floor. That's great. Now we can ask ourselves the question, well, is that a lot of pressure? And I don't really know. I don't know what that number means. I don't know if that's a big number or a small number. I just don't have a sense for it. So let's try and give ourselves a little bit of an idea of maybe how large that number is. So it turns out that if we've got a 4-ton elephant, so that's, I guess, a standard African elephant, balanced on 1 foot, then they will have a pressure of 250,000 pascals underneath that foot. So that's roughly 10 times the pressure that I have underneath my foot if I'm just balanced on my tennis shoe. It turns out that if a person is actually wearing heels instead of a tennis shoe, and they balance all their weight on a heel of that shoe, which is admittedly difficult to do, they end up with a pressure that's in excess of the pressure that this elephant exerts when it's standing on one foot. So the lesson there is that pressure is a function of not only the force, but also the area of contact. So if we have a large force in a small area, then we're going to end up with an awful lot of pressure. Even if we have a medium-sized force in a small area, we end up with an awful lot of pressure. All right, so that's it for now, and we will continue on with later videos.